Alright, in this video, we're going to move on to the next unit. In this next unit, remember, we've talked about Lewis dot structures before, so I'm going to review a little bit about Lewis dot structures real quick. And so, no, that's not a good one. I'll just go to a blank page. And so here I have a blank page. Remember, so if I want to draw a water molecule, I would need to put it in the middle, the oxygen in the middle, and then I have two hydrogens coming off. Then I need to count up the valence electrons. So this will be, what, 1 times 2, plus oxygen, which is 6, and that equals 8. Now to get these valence electron numbers, remember you have a periodic table. So let me see if I can draw a good one. So here's a periodic table. Remember, this has 1 valence electron, this has 2. Then we skip the middle, 3, 4, 5, 6. That's where oxygen is, right here. 7, 8. And I'm sorry, 7, and then this would be 8. So that's where I got this 8 number right here. I've used 4 electrons so far, so I'm going to subtract 4, and I'll get 4 left over. And so hydrogen doesn't need any more because remember, hydrogen was an exception. It only needs 2 electrons. Oh, I'm sorry, I put it 2. So hydrogen only needs 2 electrons. And so this one needs 0, this one needs 0. Oxygen still needs 8, so all the other elements are going to need 8. And so it has 2 in this this bond, and then it has 2 more in this bond. That's 4, so it needs 4 more. I have 4, so I'll put the dots. 1, 2, 3, 4. And there's the Lewis structure for H2O. We'll try doing another one. SO2. To do this one, sulfur's in the middle this time. I'll put oxygen here, oxygen here. If I look, sulfur is right below oxygen, so they're both 6 valence electrons. 6 plus 6 times 2. That gives me 18. I've used 4 electrons so far, so I'm going to subtract 4, and that gives me 14. Oxygen right here still needs 6 because it only has 2. This sulfur needs 4. This oxygen needs 6. That's 16. I don't have enough. When you don't have enough, remember you have to add a bond. So I'm going to add a bond here. And that gets me to 12. Since I added a bond here, this number is going to change and this number is going to change because they're sharing more electrons now. This will change to a 2 and this will change to a 4. 6 plus 2 plus 4 is 12. I have 12, so I put the dots. 6 here, 2 here, and 4 here. Or we call these, the ones that are on the center atom, we call those lone pairs. And the bond that's holding them together, this bond right here, this is called a covalent bond. Okay, what's a covalent bond? Let's try doing a couple more. So let's say I have N2. Well, nitrogen is bonded with nitrogen. And so I have, what? 5 plus 5, because there's 2 of them, so that's 10. I've used 2 electrons, so that leaves me with 8. Nitrogen still needs 6. This nitrogen still needs 6. That's 12. I don't have enough, so we're going to add a bond. You need to subtract 2 for every bond you make. Since I added a bond there, then this is going to change to a 4. This will change to a 4. That's 8. I still don't have enough, so I'm going to add another bond. This changes to a 2, and this changes to a 2. 2 plus 2 is 4. There's 4, so I'll put 2 dots there, and 2 dots there, and there's nitrogen. Alright, so now we kind of reviewed on how to get Lewis dot structures. We're going to move on. And so we're going to talk about how the molecules interact with each other. So intramolecular forces. That is the force that is within the molecule. And so there are 3 examples that are listed here. We've talked about these 3 before. If something's ionic, then I have a metal and a nonmetal. So let me write it just to have as an example. If it's covalent, I have a nonmetal and nonmetal. And if it's metallic, I have just a metal. That's the difference between all 3. If it's ionic, like this one, I have sodium, and it's going to give its electron to chlorine. That way chlorine has 8, and then sodium doesn't have that 1 on the outside, and it has 8 on the outside now. And so this forms an ionic bond. Covalent bond means they're going to be sharing. So as you can see, these 2 electrons are being shared between the carbon and the hydrogen. And over here, metallic, this is where the electrons are just going all over the place, making a very strong bond. You see this in like steel, gold, things like that. So the one that we're really going to be focusing on is an ionic bond. In an ionic bond, remember I have a metal and a non-metal. So I have something that's positive and something that's negative. So a +1 and a -1, for example, for sodium chloride. And so not all ionic bonds are the same. Some of them are stronger than others. So you should be writing this in your notes. How do I know if an ionic bond is strong or not? Well, it's the charge. If it has a strong charge between the 2 molecules, it's going to have a very strong attraction. So you can think of it as if one molecule has a, I don't know, +3 charge, and the other one has a +2, that's a pretty strong charge that they're going to be pulling toward each other. I'm sorry, not +2, -2. Like a magnet, they're going to be pulled towards each other. But if I have a +1 and a -1, well, their charge is good too because they're positive and negative, but it's just not as strong as the +3 and -2. And then number 2, the size of the ion. The smaller the ion, the closer they are, so the stronger the attraction. If the molecules are close to each other, there's going to form a strong ionic bond. So let's look at each of them. So how would I know between 2 is it stronger? Okay, is it a stronger ionic bond? So all of these are ionic. They have a metal and a non-metal. So comparing these two, the first thing, if I want to know if something is stronger, the first thing I would look at is the charge. I want a higher charge. So on the periodic table, calcium is a +2. Chlorine's a -1. Iron, I don't know what the charge is, but chlorine's a -1, and there's 3 of them. So iron is a +3. So looking at both of these, which one has a higher charge? This one. So this one should be stronger. So the magnetic force that's holding the iron and the chlorine is going to be a lot greater in iron 3 chloride than it is calcium chloride. Let's look at another example. This one's a +1, -2. This one's a +1 and -2. And I'm getting these charges from the periodic table. Looking at this, they have the same charges. So I can't use this one. So I'm going to use number 2, what number 2 said. And if it's smaller, then it is stronger. So I want the smaller one. So oxygen is the same on both of them. So I'm going to look at the other element. Lithium is in the 2nd energy level. Cesium is in the 6th energy level. So lithium is much smaller. It must be stronger. Looking here, this is a +2. This is a -2. This one's a +3, and this is a -1. So the charges are different. To compare the charges, I'll multiply. So the overall magnitude of it, the charges between them, will be 4. Between these will be 3. So magnesium sulfide is going to have a stronger charge, so it's going to be stronger than AlCl3. And the last one, KBr is a +1, Br is a -1, +1, -1. Same charges, so which one's smaller, Br or F? If you look on the periodic table, F is further up on the periodic table, meaning it has less energy levels, it's smaller. So that's how I can determine if it's ionic, which one will be stronger or which one will be weaker. But the main point of this whole entire unit is this part, the intermolecular forces. Basically the forces that hold 2 molecules together. So you can think of like a water molecule and another water molecule that are being held together. Here, I can actually show you. Never mind, I can't show you. But if I have a water molecule here, so let's say this is, I'll just draw it. So I have a water molecule, looks like this. And I have another water molecule, looks like this. Well, remember this side, this hydrogen is going to be positive and oxygen is going to be negative. Hydrogen positive, hydrogen positive, hydrogen positive, oxygen negative. And that comes from the electronegativity of the elements. Now, when I talk about intermolecular forces, it is the force that is between the molecules. So there's actually Since this is positive, it's going to be attracted to this negative side, just like a positive magnet is attracted to a negative magnet. Same idea. So the positive is going to be attracted to the negative, forming that intermolecular force in between them right there. And so like this one, H is going to be attracted to the O because I'm assuming H is positive, the O is negative, and they want that force to each other. And that goes across the entire molecule. So there are 5 types of those forces. We have to give them specific names, and here are the 5 types. There's ion dipole, dipole-dipole, hydrogen bonding, dipole-induced dipole, and London dispersion forces. And we're going to talk about each of them, and we're going to break it down. But before we do that, off to the side in your notes, you should write what dipole means. So dipole. Anytime you hear this word dipole, all that means is that the molecule is polar. Polar means it has a positive charge on one side and a negative charge on the molecule. So there are 2 ways something can be polar. So the first way is if it has lone pairs. So for example, NH3, it'll look like this. Well, since it has lone pairs, this is going to be the negative side, and all my H's are going to be the positive side. And so I have a negative side and a positive side. It is polar or dipole. And then number 2, if there are different elements around it. So different elements. And so if it has different elements, that'll look something like this, where I have like C, H, 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 I. And there's different elements around it, boom, it is polar. So those are the 2 ways that something can be polar, because it'll have a positive and a negative side. And so, let's go through the first one. Numero uno. Ion dipole forces. It is the interaction between ions and molecules with a permanent dipole. A dipole is a polar molecule. We just talked about that. So, it must have 2 different molecules to be ionic and polar. For example, here I have sodium chloride in water. So you can think of it as putting salt with water. NaCl in H2O. If I do that, I have an ionic compound. And water, which is polar, that is ion dipole. So as the salt begins to dissolve, all the oxygens will go to the sodium. All the hydrogens will go to the chlorine. And that's how it's dissolved inside the solution. Here's another example down here. MgCl2 dissolved in CH3OH. This is ionic because it's a metal and a nonmetal. This is polar because there's different elements, so ionic and polar, ion dipole. Next we move to dipole-dipole forces. It is the interaction between molecules with a dipole, a polar molecule with another polar molecule. So when I have something that's polar, that means I have a positive and negative end. Well, since I have a positive and negative end, this negative end is attracted to this positive end, which is attracted to this negative end over here, which is attracted to this positive, and so on and so on. So the positive is attracted to the negative of another polar molecule. So if I have 2 polar molecules like you have right here, HCl and HBr, because they're 2 different molecules, they're both polar, how can I know which one is stronger? Well, if given 2 dipole molecules, you're going to look at the distance between the molecules. The smaller the molecule, the stronger the attraction. So looking here, HCl and HBr. What's smaller? HCl is smaller than HBr because Br is further down on the periodic table. Next we have hydrogen bonding. So this one's actually pretty interesting. Hydrogen bonding you find in water and ammonia, like in the examples I have there. It's basically like dipole-dipole, which is polar, except that it's very, very strong because the molecules are super small and they're very, very negative and very positive. So looking here, if H is bonded to either N, O, or F in the molecule, then it is called a hydrogen bond. This force, this positive to negative, this force that's holding them together, like an electromagnetic magnet basically, holding both of these molecules together, that is called the hydrogen bond. I also see it in this one where it's NH3 and this nitrogen is attracted to this hydrogen. Same thing, because it's hydrogen to nitrogen. This would be a hydrogen bond as well. All right, dipole-induced dipole. It is the interaction between a polar molecule and a nonpolar molecule. So for number 4, if I have oxygen, which is nonpolar because it's bonded with itself, there's no positive side, there's no negative side. But if I mix water with it, remember, water does have a negative side and a positive side, it'll create or induce a polar molecule in this nonpolar one, where the electrons will actually go away from this negative side into this side, making it slightly negative and slightly positive. Now this force that's holding them together is actually very weak, so it's not going to be that strong, but it is a force that they have together. And so this is a dipole-induced dipole. And the last one, the easiest to remember, is the London dispersion. London dispersion is the force between a nonpolar molecule and another nonpolar molecule. So the electrons are in a state of constant motion. If you look, this is what an atom actually looks like. Because remember, the electrons are free to move in the electron cloud and they're going everywhere. Well, since they're free to move everywhere, I won't have exactly the same amount of electrons once I put a line down the middle. I won't have the same number of electrons on both sides. So sometimes some of the electrons move to one side than the other, making it slightly negative and slightly positive. Well, then this atom over here, atom B, fills that and it makes it have a slightly negative, slightly positive side. And so I'm basically getting a nonpolar molecule to have a little bit of polarity. Now this is by far the weakest one out of all of them, so this is going to boil at low temperatures. It's not going to hold very strong. But that is the force that's holding them together if something is nonpolar. So here are examples of nonpolar: He, helium, because it's just a single element, or xenon, because that's also a single element, so they're going to be nonpolar. So how can I figure out which one is stronger between the two? Well, since I'm looking at the electrons, then the number of electrons will tell me how strong it is. The more electrons I have, the stronger the attractive force. Because more electrons, if I have a whole bunch of electrons, more likely that they'll move to one side and it'll be slightly negative and slightly positive. So that was a lot of information that we covered. How do I know which is which? What do I do? I'm lost. That's what this is for. This concept map is to help you figure out what is the intermolecular force when I ask you for one example. So let's take water, for example. We already drew water earlier, so let me draw it right here. So the first thing you should ask yourself, is it ionic, is it polar, or is it nonpolar? Those are the 3 things you should ask yourself. So looking at this, water. It is not ionic because there's no metal. Hydrogen's not a metal, oxygen's not a metal. So, is this polar? Yes, this is polar. And I know it's polar because it has lone pairs. So let's go through the problem. Is there an ionic compound? No. Are polar molecules involved? Yes, that is polar. Okay, so yes. Do you have a polar and a nonpolar? Well, no, I just have one polar, so no. Is H bonded with N, O, or F? Okay, H is bonded with O, so yes. It is hydrogen bonding. So you see how it helped me flow into that one right there. Let's try another one. Let's say I have oxygen mixed with water. So here I have 2 things. I have oxygen right here, and I have water. So first let's look at oxygen. Oxygen is bonded with itself, so that is actually nonpolar. Water, we said, was polar. So I have 2 things here. I have something that's nonpolar mixing with something that is polar. So let's go through the concept map. Is there ionic? No. Is there a polar molecule? Yes, water is polar. Do you have a polar and a nonpolar? Well, I have both. Yes. Dipole-induced dipole. That's the force that's going to hold them together. Oops. One more. Let's say I said NaCl. Na is a metal, so this is going to be ionic. So is there an ionic compound? Yes. Are there polar molecules? Well, no, it's just ionic, so no. Ionic bonding, so I ended up here. So you can see how this will help me with pretty much every element or every compound I'm going to need for this. If you need to know, this one is the strongest one. Ionic bond is the strongest one, and they're actually in order where London dispersion will be the weakest one. So you should write that off to the side just to make sure you have that. I like to use this chart though, because this chart is more helpful because it helps me look at everything at one time. So if it's ionic, it is a metal and nonmetal. If I have a metal and a nonmetal, like this one, so I have NaCl or something like that, for it to be strong, I'm going to need a higher charge and a smaller size. And we did that in the very beginning of the video. If it's ion dipole, I need two things. I need ionic and I need polar. If it's hydrogen bonding, H needs to be bonded with N, O, or F, one of the three elements. If it's dipole-dipole forces, then it just needs to be polar, because remember, dipole means polar. If it's dipole-induced dipole, I need two things. I need something that's polar and nonpolar. And last one, if it's London dispersion, then it's just going to be nonpolar for this one. And I'm going to look at the number of electrons. The more electrons, the stronger London dispersion. Alright, so that's pretty much it for the notes for this video. On the next video, you're going to be looking at the examples and taking them on your notes as well. And then you'll have the practice to do. You do have a couple days to do this, so use your time wisely.